the remainder result I can get back will be at most m, right? Remember that remainder result in the worst case is going to be an array. The longest that array could be is exactly the target sum, right? Imagine that we had the most simple, sort of a combination to generate the target sum if it was just a bunch of ones, right? If my target sum was 50 and I had an array filled with 1, then I can just do 1 plus 1 plus 1 plus 1 50 times to generate the target sum. So in the worst case, this copying operation will take m steps. And I need to do that for every recursive call. And so if I have this many number of recursive calls, in addition to that, I do an m operation, you just multiply that m, right? So the time complexity for this brute force so far is n to the m power times m. Really, the thing we want to optimize away is this exponential part, right? So I really want to focus in on that. But while we're here, let's go ahead and talk about the space of this brute force. So the space, there are a few things to consider. In terms of the stack space, it's going to be the same as last time, so it's going to be O of m. If I think about any other space I use up, I guess you should also consider the array that you return back. However, we know that we're going to return back like the first array that we find all the way back up to the top level call. And the combined length of all of those arrays that we return is really just going to be, in worst case, m, right? So I would still say that the space complexity for this function is just m right now. Cool. Obviously, let's work on optimizing this time complexity. So this was the brute force. So brute force. And you guessed it, there is definitely some duplicate subproblems in this brute force. So we'll just memoize it away. So very formulaic stuff. Most of the work is always the brute force. So I'll start with my empty memo object. And like we always say, we'll use the target sum as our key. So if I've seen the target sum before, that is, if it's in the memo, then I'll return what I have stored in the memo. And at this point, what I want to do is make sure I pass along the same memo object to all of the recursive calls. That way they can benefit from any information or any subproblems that I worked on over here, right, in this stack frame. Cool. And at this point, I need to make sure that I take all of the return lines that I had before and I store them in the memo, right? So the trick here is I can say memo of target sum. I'm going to save that array. So notice that now the values in the array, or sorry, the values in the memo object are going to be arrays, because that's the return value of this. It's either going to be an array or null, right? So I'm just going to complete this return value by returning what I just put in the memo. And in a similar way, I also want to memoize this late return. So it will also be memo of target sum equals null. And I can just still return null. Cool. So with that change, right, it's a very, very straightforward change. Let's see how this does now. I know that for this last example of how sum 300, it is not possible to generate the sum of 300 using just 7s and 14s. So I should get a null for that one. So let's give that a shot. Nice, and there I have a really quick running null for that very last example. So we definitely had an effect on the runtime here. Let's talk about how we changed the complexity of this code. So that was the brute force. Let's talk about the memoized version. So what's good with the time over here? So we know that in terms of the time complexity from the number of recursive calls that we make, it's the same story as our last problem, right? We just have to consider any other time operations, which would still be this array copying. So, but in just terms of the recursive calls that we make, it's going to be n times m recursive calls. And then in each recursive call, I need to do this copying pattern, right? Copying over the contents of an array, and the array will be at most m elements long, right? So if I have this many recursive calls, and each recursive call needs to make an m length operation, then I just multiply by another m term. So right now this looks like n times m, which is the same as n times m squared. And now let's talk about the space complexity. So the space complexity will be at least as big as our brute force. So it's going to be at least O of m. But now we have to consider all the space we use up in the memo object. So if I think about the keys of this memo object, the keys are just going to be all unique values of target sum, right? Because I just literally use target sum as a key on all of these lines, right? But then I have to think about the value, right? The values are going to be pretty chunky now because sometimes a value in the object is going to be an array. And I already said that the maximal length of any of these arrays that I return is going to be of length m, right? So to me, it's now the case that your space complexity comes from mostly your memo object, which is going to be of size m times m, right? Because you have m keys, and each key has a value which is at worst going to be an array of m elements. So it's m times m, which is m squared. Cool. Notice that we definitely cut down on the brute force implementation, especially in terms of the time complexity. Obviously, there was a little trade-off that we made here, but now we're able to run our howsum function in a reasonable amount of time. So to wrap up this problem, let's go ahead and hop back into the drawing board. All right, now that we coded the howsum problem, let's wrap it up by actually analyzing the complexity of it. So recall that for our howsum problem, we have multiple arguments, right? So I need to describe them. So I'll say that m is my target sum and n is the length of the array. Remember that the array contains the choices we can take. And our baseline solution, that is our brute force recursion, had an exponential time complexity, right? It was kind of in the form of n to the m power times m. And after we actually optimized it using the memoization strategy, we actually reduced it from exponential down to a polynomial time complexity. In particular, our new time complexity was n times m squared. So a really important fact about our memoized time complexity is it is no longer exponential. Please recall that when we have m squared, that is not exponential because the exponent is a constant number. Cool. If I look at the space complexity for this, I had to actually pay a little more cost in terms of the space because of the memoized object. But that space complexity we use up is still not exponential, right? It's still a polynomial or quadratic complexity, so I'm still satisfied with it overall. So we definitely prefer this memoized complexity over the brute force. All right, that was the howsum problem, but now let's go over one more variation of it. In this problem, I'll still give you a target sum as well as an array of numbers to choose from, but this time what you want to do is return an array containing the shortest combination of numbers that adds up to the target sum. And along with that, if there's any ties for the shortest combination, you can return any of those shortest ones. So from this description, you probably recognize that this is similar to our last two problems, but now they're asking for a little bit of an optimization, right? So I want the shortest sum, so that means an array containing the least amount of numbers, but it still adds up to the target sum. So we're really just going to add on top of our previous understanding. Let's take a look at a few examples. So let's say I gave you this example. So here my target is 7, and the numbers I choose from are 5, 3, 4, and 7. So there are a few different ways you can generate your target of 7. One way would be to do 3 plus 4, that's one combination. But another way would be just take the 7, because notice that 7 is actually a member of the array. And here I want to choose the smallest array, which would be just the lone 7. So that would be the expected result for this one. In a similar way, let's say I gave you a target sum of 8, and your choice of numbers were 2, 3, and 5. There are plenty of ways to generate 8. You can do 2 plus 2 plus 2 plus 2, or you can do 2 plus 3 plus 3, or you can just do a 3 plus 5. And here I want to return always the shortest combination, which would be the 3 plus 5. So that'll be the result over here. Cool. So we definitely have some awareness that, all right, this problem is similar in structure to our previous one where I need to sort of generate a way to make the target sum, but now I want to really specify the shortest array, right? So let's try to visualize this as a tree, like always. Let's say we were stepping through this example with the target sum of 8. So we know that the full tree would look like this. And we've seen this tree before, but now what we're trying to do is come up with a different process for the value we return, right? It's no longer going to be valid to just return the first way that I find to generate the target sum. Now I want the best way. So let's start coming up with the strategy for this. At this point, we know that we can definitely implement some logic in our code where we return an array up our recursive calls. We did that in the last problem. So here we'll sort of use some abstraction to assume some return values. So let's say that I'm breaking this problem down. My top level problem asks me what's the best way to generate 8, but I see that along that path I have to find the sub-solution for the best way to generate 6. So let's say we're rooted at this subtree, and we know that there are a few ways we can make 6, right? If I look at this subtree rooted at 6, there are 2 0 base cases, downward, right? So if I look at the first one, I look at this path, I know that my subtree over here will be able to know that, all right, one way to generate 6 would be 2 plus 2 plus 2, right? We kind of implemented that logic in the last problem. But now what I also want to do is consider any other paths in case they end up being shorter. Obviously, I know that this path of 3, 3 ought to return upward. And now I have to kind of make the decision, between these two options for generating 6, I should just prefer the shorter one. So that means it's sort of 2, 2, 2 versus 3, 3. And obviously the 3, 3 wins because the array length is shorter. And if I pause right here and I look at what the diagram is saying, it does make sense that above the 6 we have 3, 3, because that is the shortest way we can ever make a 6, right? Just 3 plus 3. But now I can return this subarray to my parent. But if I do that, I should also include the value of the edge along that path, right? So I also included the 2 over here. And now this makes sense because one way I can generate 8 is 3 plus 3 plus 2, right? But we know that's not the optimal way. Let's say we step through this a little further. Let's say we took the same sort of process for this other child of 5. So I know that to generate 5, there are 3 options according to the subtree, right? Because I see 3 different leaves that have 0 inside of them. And so I know that for these paths, they would work out to their own subarrays. And here, I really just want to choose the shortest one, right? So obviously, the lone 5 wins out over here. So that would be returned all the way up to that 5 node. But then that 5 node will return it to its parent. But then, of course, I need to include the edge that connects the 8 to the 5, right? How did I transition to that 5 in the first place? So I go ahead and just add it in. And now the root node over here has a decision to make. Which one does it prefer between 3, 3, 2 or 5, 3? It'll just choose the shorter one, so the 5, 3 should win out over here. And I just need to continue this process for any other branches in my tree, right? I can't return early in this type of problem because I need to find the optimal way, and I can't be sure until I've tried every possibility. Cool. So it looks like our overall logic is we want to explore and find any ways to generate our target sum, but then when we find a way that's shorter than our currently tracked way, we can just replace it. I'll continue that process through the entire tree. If I check every possibility and keep replacing what I consider the shortest, by the end of us exploring every branch, we would have the absolute shortest. All right, I think we're ready to hop into the code. All right, programmers, welcome back to my text editor. Let's work on coding this one out. So here I have some initial examples that we'll use to test our best sum function. Notice for this last one, right, I give my initial target sum of 100, and the best way to do that is obviously just take a bunch of 25s, right, 4 25s. And what I also want to bring our attention to is this third example over here. So my target sum is 8, and my choice of numbers are 1, 4, and 5. The optimal answer here is 4 and 4, right? That is the shortest way to generate 8. A common mistake I see a lot of students make is sort of assume that the best way to generate the target sum always involves taking the largest choice of number as many times as we can, right? That is not true. If you took a 5 in your sum, then you would have to take 3 ones in the long run, which is not going to work out to the shortest answer, right? So it's not the case that just taking the biggest choice of number always yields the target sum in the shortest amount of numbers overall. So don't fall into that trap, which means that we have to do the full tree exploration, right? We have to do an exhaustive sort of search using our recursive code. And so let's start with that base case like we always do. So I've written this a few times, but I'll still write it here. So if the target sum is 0, then I have trivially solved the problem, so I can just return an empty array, right? That is the exact single combination and the shortest combination that can generate the target sum. Cool. Along with that, let's handle that scenario if our target sum goes too far downward, so if it's less than 0. So if the target sum is less than 0, I'll just return null, meaning that it's not possible to generate that target sum. And now we'll use our branching logic. So I'm going to iterate through all choice of numbers. So I'll say for let num in numbers. And like we always do, I'll go ahead and create my remainder, which I know would be the difference between my target sum and that choice of number. All right, so what I'm doing is I'm choosing the number, and that decreases my target sum. At this point, I would make my recursive call, right, with that remainder, passing in the same numbers array. But now I have to do some thinking. I know that, all right, best sum is either going to return to me a combination or an array, or it's going to return null. So I'm going to have to kind of differentiate between the two. So over here, maybe I'll just save this as a result. I'll call this my remainder, let's say combination. And if this remainder combination is not null, then I can do some other logic, right? So I'll say if the remainder combination is not equal to null, then do stuff. So if I enter this if statement, then that means it is possible to generate the remainder. And exactly what remainder combination is an array containing the shortest way I can generate the remainder. Cool. So if I enter this if statement, then I also have a way to generate the full target sum, right? I can just take the remainder combination, copy the elements over from it like we did last time, and also add on the choice of number I just took, right? So this would be now a complete combination for target sum. So I'll just save that as a regular combination. Cool. So far this is very reminiscent to our last one, and we need to work in some more logic relevant for this problem. That is a very, very important characteristic that we needed to implement in the tree was I need to sort of choose the shortest combination, right? So I'm going to need to work in that logic. So here's what we can do. I know that I need to compare basically all of my branches together, all of my recursive calls together, and pick out the shortest combination. So I know that this for loop is the piece of code that sort of iterates and attempts all of my branches. And so outside of the for loop, I'm going to need some outer variable. I'll call it my shortest combination. And over time, I'll just keep updating this variable if I find a combination shorter than my current shortest combination, right? So I'm going to initialize this to null. And the reason is, imagine that we set up this shortest combination variable as null, and then we iterate through the for loop, and there isn't even any way to generate the target sum. So this for loop finishes, and shortest combination would still be null, and that'd be great to return, right? Because in this problem, they said if it's still not possible to generate the target sum at all, you should still return null. So this is a good initial default value for shortest combination. But now I need to do my update logic. So here on line 11, I've actually created a combination that gives me the target sum, but now I need to check, right? So I'll say if the combination is shorter than the current shortest, then I need to update it. So to translate that into some code, we just use an if statement, and I'll start by checking if the combination that I currently have, which is an array, right? I check if that is less than in length than the shortest combination variable. And really, it looks like shortest combination, it starts as null, so I need to fix this code up a little bit. But if I update it with a valid combination, then it's going to be an array, right? So I'm really checking the length of the arrays here. So what I want to do is assign my shortest combination with the combination that is now shorter. Good. So this means the shorter combination wins out and gets to stay, right? If I look at this code, it needs a little bit of work because the first time I find some combination, I know that I'd be comparing that array length to null.length, right? Because shortest combination starts as null, and I can't do null.length in JavaScript. So I'll need like a nice or clause here. So I'll say, if it is the case that your shortest combination is equal to null, then you can go ahead and replace it. Cool. So this sort of check over here is going to make sure that I automatically replace this null value with the first valid combination, even if right now it may not be the shortest, right? Later on, I'll compare that combination I have stored to some possibly shorter combinations. Cool. So this code is looking pretty good. Let's go ahead and give it a little test run. Nice. Notice that on occasions where we call best sum with a remainder that is negative, because remember, sometimes we subtract a num that is maybe too large, that's okay because that will actually bottom out at a base case and return null, which we sort of check for explicitly in this if statement. Cool. So let's give this code a run. So node best sum. So I get an error over here. Looks like I get maximum call stack size exceeded, which means that we didn't really hit our base case. So there's some work to be done here. So let's take a look at this code. So if I take a look at this code, it's a very, very small typo. It's kind of unfortunate that it breaks the entire code. But it's really, I messed up when I iterated in the for loop over here. So here I wrote for let num in numbers. That would actually give me the indices of the array. So that'd be like 0, 1, 2, 3. Whereas I want the elements of the array, right? So instead of in, I need of over here. So that's on me. So with that small change, let's give it a run now. Yeah, it looks like we're passing these first three examples where I have 7, 3, 5, and 4, 4. Notice that the order among the elements in the combination doesn't really matter too much. But looks like we're definitely a little too slow on this last example over here. right? So obviously we know the move is to memoize this because we have the brute force recursion. But before we do that, let's just talk about the complexity of this. So this code is going to be very similar in complexity to our last howsum function. And we sort of compare the two. It's almost the same code, right? If I do these side by side, right? These two functions look very, very similar. So we know in the long run, we'll probably have the same or close to the same complexity. But let's be methodical. So we know that over here, we always like to say that M is the target sum. And then we'll also go ahead and say that N is the numbers dot length. So we just did the brute force. And our brute force should be the same story as last time. So we'll talk about the time. So the time of the brute force is going to be some sort of exponential, right? If you remember that tree drawing, in general, the exponential number of nodes in a tree will be the branching factor to the height power. So I know that the branching factor here is n, right? I branch for every choice of number. And then the height of the tree would just be the target sum, so that's n to the m. But along with that, we also have some additional operations, right? If I look at this for loop, so this for loop gives me the branching factor, right? But then I also do this operation on line 11, which is copying over the array of remainder combination. And that array in the worst case will be of length m, right? The largest sort of a combination give me back is a combination that is just filled with a bunch of ones, right? If my target sum was 50, the longest combination possible would be a bunch of ones, so 50 ones in an array. So what I'll do is I'll say that for each of these n to the m power calls, you also have to do a linear operation in m, right? So like before, it's n to the m times m. Cool. And then the space complexity is sort of interesting in this one because we're maintaining some values. So look at this. So if I talk about the space complexity just from the stack space, it would just be the height of like the recursion. In other words, it would be m over here, right? So I know it's going to be at least m. So I'll jot that down. But then we have also like this variable on line 5, right? So I know that over time, I'm going to be storing an array inside of this variable. And this array is going to be, in the worst case, m in length, right? So what I'm saying is every recursive call would have to have its own shortest combination variable, right? If the shortest combination variable is going to be an array of length m, that means I have an array of length m for every recursive call, right? Before I bottom out at like my final base case. And so I'll say that the space complexity here is m times m, which we know is the same thing as m squared, right? And sort of the reasoning is your maximal stack depth is still m, like last time. However, now in each of those stack frames, you need to store an array, right, as you recurse. Nice. So really, the limiting factor for us right now is going to be the time complexity, which is exponential. And so like we always say, let's go ahead and memoize this. So memoization, pretty trivial right now, right? You've done it many times. So I'll just bake in my initially empty memo object, and I'll check, if my target sum is in the memo, then I should actually return the stored value. So return memo at target sum. So now that I have my memo checking logic, what I also want to do is add the memo storing logic, right? So I need to just go to my return value and store it in the memo before I return it. Notice that the return value right now, it's no longer inside of the for loop, right? In the last problem, it was in the for loop because I can return early. But this time, we're going to return at the very end. So I'll replace it over here. So I'll say, for here, the memo at target sum should be stored with the shortest combination. And I can still return the shortest combination. And before I forget, let me go ahead and pass down the same memo object by reference. All right, nothing too much to that. Let's go ahead and try this last example now. Let's give it a shot. Awesome, and there we have it. We have 4 25s in this last example, and that is the best way to generate 100. It is pretty evident that we cut down on the runtime. So let's talk about the memoized complexity. Memoized, and so the time is obviously much faster, should not be exponential. But if I take a lay of the land, I know that now every target sum is going to be a key of the memo object, and target sum is really just a number, right? So if my target sum is 50, then I basically have 50 different keys I can ever store in the memo object. So if I have m different keys in my memo object, I know that I won't be exploring any full duplicate subtrees for each of those keys. However, I will still have to branch for every number in the array, right? So overall, I'm looking at an m times n So far I have m times n, but I have some additional work from this array, right? So notice that the n over here, that comes from this for loop. I'm iterating through numbers, but then the additional m comes from copying over this array, which would be linear. So it would be m times n times m, and I can just kind of squish these two m's together. So it kind of boils down to m squared times n, which is really the same thing as last time. And our space complexity would also be the same as it was last time, which was just m squared, mostly coming from the memo, right? And the logic is your memo keys have m possibilities, but for each of those keys, their value can be an array of length m, right? So just m times m or m squared. Awesome. So looking at this code, you're probably, feeling that, oh my gosh, like this best sum problem is pretty complex. And I think it, to be honest, it is. However, what I really want us to focus in on is this like progression we took, right? I think that everyone could tackle this best sum problem if they warmed up and really understood simpler problems like can sum and how sum, right? The code is very, very similar. So to wrap things up, let's do some closing words on the drawing board. So in this best sum problem, right, we had two inputs. We had m as our target sum. I'll also say that n is the length of the array. So the brute force that we initially implemented with just some recursion was exponential in time. And after we optimized it, we brought it down to just a polynomial time complexity. And notice that between our brute force and our memoized solution, they actually have the same space complexity. So we definitely prefer this memoized version. So I hope you enjoyed this series of problems. That is, we worked on the can sum, how sum, and best sum problems. They all had the common frame of us having some target sum that we need to generate with some options given in an array. And in particular, if you look at the can sum problem, it asks us with that task of generating the target sum, can you do it? So yes or no. The how sum problem asks us how will you do it? So what are the exact combination of elements that you'll use? And then finally, the best sum was the hardest version, and it asked what is the best way to do it in terms of the least number of elements of the array. So there definitely is a logical progression to these problems. And in particular, they kind of capture a different variation of a dynamic programming problem. For our can sum problem, right, we had to return Boolean there. That's a type of decision problem, right? Yes or no, can you accomplish this task? Is it possible? Along with that, the how sum problem was a combinatoric problem, right? We want to know the exact combination that works out. And the best sum problem was a variation of an optimization problem, right? I want the shortest way to generate the target sum. We saw that these three problem types definitely have some common ground, but they also have some nuance depending on exactly the question we're trying to answer. And these all fall under the umbrella of dynamic programming. That being said, dynamic programming problems aren't just limited to number inputs. All right, I think it's time to work on another prompt. Let's say I gave you this. What I want to do is write a function called canConstruct that takes in some target string as well as an array of words in a word bank. My goal is to return a Boolean indicating whether or not I can make the target by concatenating together elements of the word bank. And along with that, we can reuse as many elements as the word bank as we see fit. All right, notice that in this problem, we're looking for a Boolean response to start, right? So just yes or no, is it possible to generate the target? So let's take a look at an example here. Let's say I gave you this. So my target is A, B, C, D, E, F, and I have a nice long array of some words. And so I'm basically asking, can you construct A, B, C, D, E, F using elements of the array? So if I kind of take a look at the array, there is exactly just one way to generate the target string, which would just be ABC plus DEF. So the answer here is true because there is at least one way to make the target, right? Let's take a look at the opposite example. So let's say I had this word of skateboard, and I gave you all of these words in an array. So take a moment to kind of look this one over, and you tell me, right, is it possible to generate skateboard here? And the answer here is no, right? It is not possible to generate skateboard using this array of words, so we should return false. We can get pretty close to making skateboard, but we can never build the full string, right? So here are a few ways that we can attempt, but they don't work out in the long run, right? This is one series we can take, but we kind of get stuck, as well as this, and also this way, right? Point being, there are 0 ways we can ever generate skateboard, so we should return false over here. Awesome. So I think let's look at one more example. We should already have the vibe that in general, it's easier to create a shorter string than a longer string, right? To create a longer string, you're probably going to need to use more elements. So if I have that kind of framing in mind, then I know that possibly the easiest string to create would be the empty string. Right, so let's say your target was the empty string, and I gave you, some kind of random array of words. Really, the array of words doesn't really matter here. I think no matter what, this should return true. Because to generate the empty string, you can just take, 0 elements from the array. And that kind of line of thinking is going to help us really start to solve this problem. So we'll kind of take this example in stride. What we want to do is return true if our target is empty. And that takes place no matter what array of words we're given, right? Cool, more or less, that kind of sounds like a base case, right? But let's go ahead and start to kind of define some process we can take to explore all of the options, right? So I want to really visualize this in a well-ordered way, and that really means a tree, right? So let's say we're going to trace through this example visually. So my target is A, B, C, D, E, F. And we already said that in the long run, we should return or conclude a true about this input, right? So we'll just start with the input argument that is the target string as the root of this tree. And this is sort of a scenario where like, all right, I have 2 inputs. How do I know which one to really encode in my drawing? Well, it's about what will actually change. I know from like one instance of like this problem to the next, the array of words, I can actually reuse as many times as I need. So it's not like I'm taking out elements from the array. So with that in mind, I think it's better or more reasonable to encode the actual target string into the nodes of this picture. Cool, so I'm going to start with this original target string on my root. Now I have to think about how I transition to the children of this, right? So what moves do I take that hopefully shrink the target string, right? I know I need to shrink the target string because I already have the base case of the empty string in mind. So I need to get closer and closer to a length of 0. Let's talk about one transition we can make. So I know that I need to sort of use the array of words as I transition. And so let's say I took AB as a choice right now. If I take AB, then I guess I could remove, that sequence of characters from my parent node. So if I take AB out of A, B, C, D, E, F, then the resulting child is just C, D, E, F. Cool, so notice that as we transition from one node to the next, it looks like we're taking out that substring. In a similar way, I have another substring that I can take out from my word bank, and that would be ABC, and that would yield in the child DEF. And then I can do this for some other string inside of the word bank. And the really important thing to know is there's a correct logic to doing this, and there's also a common trap I see a lot of students fall into when it comes to this logic. So right now I'll talk about like the common mistake. So it would be ill-advised to sort of take out the CD from our root node. If you took out CD, then the resulting node would be ABEF. And so what we're doing right now is if we took out CD, you're taking out something in the middle. And if you take out something in the middle, that means that your resulting string actually creates a new adjacent sequence of characters. In other words, I know that this is kind of suspicious because if I look at this little run of characters, ABE, those are now like adjacent next to each other. Whereas in the original string of ABCDEF, ABE was not present, right? So if I kind of take out strings in the middle, then I'll have this sort of mistake of creating new adjacencies, right? And that would actually impact the moves I take later on. So I don't want to do that, right? So the move here is to not take out any characters from the middle of the string. So what would be the correct way of doing it? Well, if you look at our 2 nodes that we already branched into, a common factor for them is the fact that we actually took a prefix out of our original root node. That is, AB is a prefix, and so is ABC. Recall that a prefix is just a string that kind of begins some other larger string. So if I want to transition to a third node over here, there's only one more prefix I can take, and that would just be ABCD. Right? And if I take that prefix out, then my resulting child is just EF. And so the overall logic that we want to use when we build this tree is to only branch to children if we have a matching prefix in the word bank. And of course, the child would be the resulting string after we remove that prefix. So let's keep it rolling, and we'll apply this logic again and again recursively. So let's say I'm rooted at this CDEF node. I'll look inside of the word bank and notice any prefixes that actually match here. I think there's only one, and that would just be CD. If I took out the prefix CD, then my result is EF. In a similar way, I can do that for DEF. I find that DEF is actually contained in the word bank, so it's technically also a prefix. If I took the prefix DEF out of that node, then my result would be empty, which is pretty good. At this point, I look at some other nodes like this EF, and they have no matching prefixes inside of the word bank. So they sort of bottom out in some sort of base case. In the long run, if I can't break down EF any further, then I know that it's not possible to construct EF. So that can technically return a false to the parent. In a similar way, if I ever run into the empty string, that means the job is done and I can just